approximation that you got is basically talk about what? The net area. So the net area can be what? A negative value or a positive value, depending on the area under the curves, right? Is above the x-axis or below x-axis, which one is bigger? So using that, what we're going to do is we're going to define the definite integral. Okay, we're going to look at a definite integrals and we're going to look at indefinite integral, right? So definite integral is going to give you a value, a numerical value, because we have an interval to evaluate from which interval to which interval. The indefinite integral that we're going to look at later on will give you an expression. Okay? And that expression has a meaning to it, which is a big important idea to connect between differentials and the integral calculus. Okay? So, definite integrals. So if you look at this, giving you a function, and that function is in between a to b. And dividing into n subinterval, so therefore our delta x, which is the increments, equal increments, will look like b minus a over n. Right? B minus a over n. With the initial, the beginning point x sub 0 as a, and then the end point will be the end of the interval x of n equal to b. Any subinterval that we talk about in between, okay, the area of those rectangle will be denoted by now what we call it integral, definite integral of function f from a to b. Using this integral notations, right here, that's the integral notations, and the interval that we write down is the lower bound of the interval and then upper bound of the interval, and the function that we are integrating, this function is called integrand of dx. That basically tells you are integrating, right, respect to which variable. Because remember, you're going to be going into multivariable later on, right? So the respect to which you're integrating respect to which variable, first, second, third, that is very important. Right? So this is called the variable integrations. Basically talking about, what is the independent variables going to be in this integrand. And this new notations will be defined by something that we know. Okay? But this time, we are talking about what? Not finite case anymore, the infinite case. Okay? We want to talk about infinite case. Means that the rectangle will be, there will be infinitely many rectangles such that, it will give you exactly the same area, almost. So limit as x n approaches to infinity. Notice that your subinterval is infinitely many, and this is basically the Riemann sum, which is the net area of this area under the curve on this particular interval. So, any questions on this new notations? What we're talking about? It's basically what we learned previously. We just giving a new notation right here, and this notation has a meaning to it, which is what? The net area, because we want to talk about the area above and then below the x-axis altogether. Are we all okay with this? Now, this net area, which is the definite integral, okay, can be approximated with the midpoint rule that we talked about before, the left endpoint, right endpoint that we talked about before also. Okay, and what we want to do is we want to find out not approximation part. We're going to do a couple of example approximation part again, but mainly what we want to find out is what is the exact value is going to be, right? Close to what is it? Close to exact value going to be. So that requires something that we learned in pre-calc. Okay? What is summations of I equal to 1 to n of I? What is that formula equal to? What is I squared? Summations of I squared equal to? What is summations of I to the third power? That is equal to. And plus sum of the summations property, which is if you have summations of the same number, a constant number, n many times. So that will be just basically what? Addition is repeated addition is the same thing as multiplication. So that's why n times. And when you have a constant times with a function, right? A of I is considered as a function. So this is like this situation. Notice that delta x is a constant all the time, so we can factor that delta x out. So therefore, right here, summations of a constant times a function, that is basically talking about constant times with the summations of the function. And the summations notations, if you are talking about summations of sum of two functions or difference of two functions, then we can talk about each function, summations of each function, and then sum them up or make the difference. So these are the properties that we learned from the pre-calc. So these three things you need to remember. Okay. In the pre-calc, we sort of prove these by induction, right? Proved by mathematical inductions. We do that. And last semester when I was teaching pre-calc, I did that, but it was like very at the end, so a little bit rushed in that class. But did it. So, any questions before I move any further from here on these recall? Okay. If not, then what we're gonna do is we're gonna use these very soon. But let's try to do the first few problems that we sort of did it last time, right? In the last sections, but you're looking at different notations now. So now, I want you to evaluate the Riemann sum, right? And using the right endpoint for this particular functions, and also asking you to interpret it. What is this Riemann sum representing? So, first step that we need to find out is what is my delta x's. So that will be my integral is from a equal to 1, b equal to 4, right? And then the increment that we want is 6. So my delta x will be equal to 4 minus 1 divided by 6, which is 1/2, 0.5. And then we want to talk about the right endpoint. So the Riemann sum, okay, for the right endpoint, so R of 6, that will be summations of I equal to 1 to 6 of the function xi times with delta x. So which is, in this case, 0.5 times with the right endpoint. So the very first point that we're going to be using is 1.5, 2, 2.5, 3, 3.5, and then 4. That will be my right endpoint. 6 subinterval. when you evaluate this, plug it into the functions and evaluate it, that should give you approximate answer. So go ahead and do that for me, because I did not calculate these number. So calculate it quickly. If you have TI calculator, it's even faster to compute those.
Professor, this was going to the right?
Yeah, we are using the right endpoint.
Yeah, okay. So you
So
don't...
that, yeah, go ahead.
1 through 4. You, 5. So 1 through 4, you divided by 4 or 5? 1, 2, 3, 4, 5, 6. Oh, by 6. That's right.
Because it's telling you the subinterval is what, 6 subinterval, right?
Yeah.
So that's why you divide it by 6 to get your delta x, which is the width of what each rectangle, which is the increment's gonna be, right?
Correct. So let's say if we were going to the left, then we wouldn't use the 4, right?
You're still gonna be. What do you mean by using 4?
Like if it said taking the sample points to the right, I mean to the left.
Mm-hmm. Left endpoint. Then
Yeah.
it will be the same thing, but however, you're gonna be starting with 1.
1. Okay.
You're gonna be starting f of 1 instead of f of 1.5. Because your interval never changed. Your interval never changed. Okay? Your interval is always from 1 to 4. That never changed. But when we make it sub-interval, right, like this, so it's basically you're gonna be, this is your x sub 0, x sub 1, right?
Mm-hmm.
So this is increment is 0.5, so it'll be 0.5, 1.5. So if you look at your rectangle like this, right? If you talk about right endpoint for the first rectangle, that means what? My height of the rectangle, I need to evaluate it what? 1.5.
Okay.
If you talk about the left endpoint, then if you look at the rectangle, then what? I'm going to be evaluating at what? My height of rectangle at what? 1 for the first rectangle.
Correct.
So that's the difference between left endpoint and right endpoint.
Okay. Yeah, got
And
it.
also the value will be different based off on what the function is increasing or decreasing.
Okay, sounds good.
Clear, right?
Yes.
Good. So, anybody get the number yet?
I got negative 2.125, but I did it kind of fast, so I don't know.
Negative 2.125.
Yeah.
Right? Approximations. Confirm, someone?
Yeah, I got the same.
Okay. So, let's take a look at this. We don't need to, blindfoldly accept our what was the function?
X squared
Y equal to x squared
minus 4x
minus 4x
plus 2.
plus 2.
Mhm.
So notice that within interval, within what? The interval of 1 through, right?
Mm-hmm.
1 through 4. Notice that the area below the x-axis is more than the area on the above the x-axis right here. So definitely the net area that we're gonna get, the Riemann sum, will be what? A negative value. Just by looking at the picture, you can sort of like see that, okay, the answer sort of makes sense. Follow? Are we all okay with this? So let's continue, right? Because so now the next one is basically, I'm not gonna do this problem, okay? This example number 2 is just basically helping you to see what is a notation and how you should write it down. Notice that this definite integral right here, right? Definite integral, the notation is given to you. The actual definition for definite integral is this. Limit as n approaches to infinity or summations of I equal to 1 to n of f of x times delta x. See, this portion right here, n approaches to infinity. That will give us, the definite integral will give us, what is the almost exact net area of this particular functions in a certain interval. Right now, this problem is asking you to use the midpoint rule to approximate this integral. Okay, approximate this interval. So what's happened is, if you're going to be writing this, then it's going to be wrong for this particular problem. You need to understand the difference. Why? Because the midpoint rule asks us to use not infinitely many subinterval, only 6. So again, all of them will be the same. The lower bound is 1. Upper bound of the interval is 4. So this notation basically helps you to see that what is my interval is. And with this n equal to 6, again, we have a delta x is equal to what? 4 minus 1 divided by 6, which is 0.5. Now, using this, the proper way of writing will be 1 to 4 of x squared minus 4x plus 2 dx is approximation not equal to. These twos are equal. Okay, these twos are equal. Those are not approximations. So right now we are approximating with the midpoint rule with 6 increments, 6 subinterval, 6 equal subinterval. Are we all clear on what I'm pointing out? What is the definition is? Right, and what is the difference between this? So this approximation is just basically what? Summations of I equal to 1 to 6. See, that is a finite of f of xi bar, that's average for the midpoint, times with delta x. And you basically plug it in, 0.5 times with, you plug it in all the average of it. So 1 and 1.5 in the middle, that will be 1.25. I basically use the same interval for this different function. It's just basically what I don't want to go back and recompute these midpoint. That make it easier for our example to move faster. Are we all okay with this? So 1.75, and then functions evaluating at 2.25 plus function evaluating at 2.75 plus the function evaluating at 3.25. Lastly, plus function evaluating at 3.75. And that will give us approximate answer right there. And notice that we are talking about the same functions, right? But this time approximating with what? The midpoint rule. So the answer should not be that much further. Okay? So tell me the numerical value for this one, if someone computed.
Negative 3.0625.
Negative 3.0625.
Yeah.
Last questions. This time, what we want is we want exact value. So that means our subinterval will not be a finite case anymore. It will be using infinites. So make sure you pay attention on the differences, okay, on this problem. So in this case, my delta x, which will later on will become the same thing as like x, that is basically 4 minus 1 over n, because my n is infinite, so we don't have a value to it. So my delta x will become 3 over n. Okay. Now, according to the formula, the integral from 1 to 4 of x to the second power minus 4x plus 2 delta dx, that is equal to limit as x approaches to infinity, n approaches to infinity, the summations of I equal to 1 to n of f of xi times delta x. So in the formula, I give it to you with this xi with a star on it. Go back and look at this. See xi with a star on it. That sample point, that's what we call it. This sample point can be used as right endpoint, left endpoint, or midpoint. Doesn't matter which endpoint you use or midpoint that you use, because of the subinterval is infinitely many subinterval, right? The left endpoint, right endpoint, all the overestimating and the estimating will be very, very tiny, such that, okay? Because if you think about it, if you imagine this, if you're using like infinitely many rectangle, very, very tiny one is almost close to like, one single line, then the error that we're gonna get is like almost, negligible, and then can be looking at as where this limit's gonna be approaching, which is the actual area. So therefore, when we're using this right here, it is your choice of you're going to be using the left endpoint, the right endpoint, or the midpoint to approximate it, okay? If I don't specifically say it. So what I'm going to do is I'm going to use the right endpoint. So how do we find out the right endpoint? Right? So this is the important part that, you need to be able to write it, because there will be one problem on the test, something like this. So how do I know how to look at x of I? How do I formulate this part? So take a look at on this right here. I'm going to give you in general, right? In general, this will be a and this will be b, my interval. The very first increment that you get, that will be x of 1. That x of 1 is always your a plus what? Delta x. Do we okay with that? Do we agree with that? Are we all okay with this? And the second increments right here, x of 2, that is another delta x that you added. So this portion right here, it will be what? This x of 2 will be represented by a plus 2 delta x. Does that make sense? And if I continue, right, if this is like the third one, x of 3, then that will be talking about what? A plus 3 delta x. So therefore, you are talking about what? 1, 2, 3 incrementing. So when you write it down for the right end points, that will become a plus I times delta x. Because in the summation notation, your I will be changing from 1, 2, 3, 4. And as change it, we are talking about what? the first, second, third, so on and so forth, those rectangle increments. So therefore, for this one, this will become my A is 1 plus my I times my delta x is 3 over n. So that is the portion that we're going to be using. Okay, so now the next step will become the limit as n approaches to infinity, summations of I equal to 1 to n, and f of 1 plus 3ni times which my delta x is 3 over n. Since the summation is a function of I, right? I is the one that's changing. So 3 over n, as usual, we will consider as what? A constant, right? You remember the delta x is a constant in before. So I can basically use the limits, right? The summation formula to factor that out. 3 over n times with summations of I equal to 1 to n of f of I plus 3 over ni. Now it becomes like, a careful computational part after we can substitute this. So what is the important part before I move on? The important part is being able to find out what is your delta x's and being able to find out a general, right, formula to write it down your right endpoint. So now this will become limit as n approaches to infinity of 3 over n times width. This is where I'm going to put this. This 1 plus 3 over ni, that will be evaluating into our function. So our function is input square minus 4 times the input and then plus 2. And this is where I'm going to have to simplify it and then find out my limits. See, now I can talk about what, now take a look at this. This is everything is in terms of n now, right? Not yet. Everything is almost in terms of n. Because limit, what we are doing is where we are finding out the limit as n approaches to infinity. I'm missing something. Yeah, I missed it on my summation notations. Okay. I missed out my summation notations. I equal to 1 to n. So, limit as n approaches to infinity, 3 over n. Now, because we want to find out the limit as n approaches infinity, so everything right here must be in terms of n. So how do we simplify that? First, simplify inside. Summation of I equal to 1 to n of, when I multiply it out, this 4, this will be 1 plus front time, these two multiply and double it, which is 6 over n I plus, and then the last square, which is going to be 9n square I squared, minus 4 minus 12 over n I and plus 2. Now, simplifying a little bit further on this one. Limit as n approaches to infinity of 3 over n times with summations of I equal to 1 to n And notice that right here, 1, 3, minus 1 will be negative 1. Nine n square I square. And here's I have 6 over ni, and then here's minus 12 over ni, so that will give you minus 6 over ni. So now what I can do is I can use the sum and differences of the summations to split this out. So that will become limit as n approaches to infinity of 3 over n times with summations of I equal to 1 to n of 9 over n squared I squared minus summations of I equal to 1 to n of 6 over ni and minus summations of I equal to 1 over n of 1. Then using the next property, right? Notice that in this summation, the summation as what? I as a function right here. So I is the one that is changing. So this 9 over n squared is a constant. So therefore, we're going to be using, right, one of the property that we learned from the past, this one, to rewrite it. So this will become limit as n approaches to infinity of 3 over n. That will be 9 over n squared times with summations of I equal to 1 to n of I squared minus 6 over n summations of I equal to 1 over n of I minus summations of I equal to 1 over n of 1. And why do we rewrite it? Because this is a formula that we can use, and this is a formula that we can use, and this is a formula that we can use. So let's take a look at the formula, right? So notice that summations of I equal to 1 to n of I squared, that is equal to what? 1 n plus 1 and 2n plus 1 divided by what? 6. So now we can get one step closer to our goal, because we want everything in terms of n, because we need to find out the limit as n approaches to infinity. So 3 over n times 9 over n squared times with what? n plus 1 times with 2n plus 1 over 6 for this particular one. Are we good? And then moving on, minus 6 over n, and according to the formula, this summations of I equal to 1 to n of I, that is basically times with n plus 1 divided by 2.
Take off from.
And finally,
Roman, take
the
off.
last part, minus summations of I equal to 1 to n of a constant, that is basically n times that constant. Now we have everything in terms of n, which is, the limit that we can find. So simplify further. Limit as n approaches to infinity. Let me stop a second. Are we all okay with this so far? If you are the first time seeing all of these notation, then you will be like, what the hell is happening? But it should not be new to us on these summation notations, but we don't see this much, right, in the past.
I'll be okay. You can keep going.
You're all good, right? The rest of us? So 3 over n times what? Now simplifying it. And that's where you're going to be like, thinking about how you're going to work on this, right? To make it fast or slow. 9 and 6 is 3 over 2. N and n cancels it out. Right? So there's basically times with right? N in the denominator. When I multiply this out, it'll be 2n squared plus 3n plus 1 when I multiply these two out. Minus 6 and 2, that'll give me 3. N and n cancels it out. So that will become 1. N plus 1. And then minus n. Continuing this, limit as n approaches to infinity 3 over n. 3 over 2 times what this will become 2n plus 3 over n plus 1 over n. Oh, plus 3, my bad. And then minus 3n minus 3 minus n. Okay, so far? Computing this. Where am I going? I'm trying to simplify enough such that I can use this theorem that we talk about in 3.4. Notice that as n approaches to go to 0, right? I should say that n to the x power. As long as the x power is what? A constant, right? Then we can have a bigger denominator which will go to 0. So that's what we are trying to use. So if you look at this, continuing this, I can simplify a little bit further. How do you want to simplify right here? It's really up to you. Right? I've seen that some students simplify very fast, right? Even faster than me. But right now I'm going step by step so that you can sort of see where we're going. And you can play around with yourself later on. Okay? So what I'm going to do is I'm going to try to distribute this and then simplify further. Okay? So 3n, and take a look at this. When I multiply these two, that will be 3n. And this 3n and this 3n will be gone. Let me just write it down. That is better. 9 over 2 plus 3 over 2, 1 over n minus 3n minus 3 minus n. So you notice that this 3n and this 3n will be gone. And you can simplify this 9 over 2 and then 3 over negative 3. So finally, so the simplifying part is the one that you after you understand these steps, the simplifying part is the one that you need to be careful. So limit as n approaches to infinity of 3 over n times with these two number, that will become 3 over 2 plus 3 over 2, 1 over n. Right? And then this n is left off minus. And then finally, something that we want, 3 over 2 times 3 over n plus 3 over 2 times 3 over n squared. Notice that I'm distributing it. And then minus, when I distribute it, that will become 3. And then we can talk about the limit on each case. So that will be 9 over 2 times the limit as n approaches to infinity of 1 over n plus 9 over 2 limit as n approaches to infinity of 1 over n squared minus limit as n approaches to infinity of 3. This will be 0, and this will be 0, and minus 3. So the actual value, net area of this function on this interval is negative 3. So you can see that the midpoint approximation is pretty close to the actual value that we have. So this is basically using the definitions of the definite integral, which is another way of saying evaluating with the Riemann sum. Okay? Limit as n approaches to infinity of Riemann sum. Questions? Difficulties?
Can you slide it to the right side again real quick?
Sure. Any portion that didn't really catch it? I'm more concerned of on these steps when I'm doing manipulations, right? How do I move from here to here? That's important. And then also important thing is, why do we need to change everything in terms of n? Because we are talking about what? The limit as n approaches to what? Infinity. So I need to have all the variable in terms of n for the function. Questions, difficulties before I move forward on the properties of integral, which you will use later.
For the formulas, it's just summation formulas, right? That's what I...
Yes.
Okay.
The summation formulas you need to remember. And if you understand the summation formula, then the properties of the integral that we're going to talk about, right, definite integral that we're going to talk about in the next page, it fall out the same thing, because the definitions of the definite integral is using the Riemann sum. So pretty much it's applied almost the same.
Okay.
So once again, 1, 2, 3 is a must that you need to remember. And 4, 5, 6, 7, you need to know how to apply those. Right? So, looking at this properties of integral, now here's the interesting part right here. Okay, if you flip around your right at this point, at this property, I cannot really maybe I can tell you, but this is what I want you to remember. If you flip around your lower limit and upper limits, your definite integral will have an extra negative sign. So that's why these two are equivalent with the extra negative sign right there. So that's the important part, right?
Where were you pointing at?
Right here. See that my limit is b to a, meaning that upper limit happen to be the small one and the lower limit happen to be the big one, the bigger number. And if you want to rewrite it properly, lower limit as a small one and upper limit as the big one, or vice versa, it doesn't matter. In the definite integral, if you flip around the limits, upper limit and lower limits, then you will have an extra negative sign in the answer.
Okay.
Follow that?
Yeah.
And I can explain that to you easier after we talk about fundamental theorem of calculus. So I'm not gonna jump into explaining why this happened. Okay? Because after we talk about fundamental theorem of calculus, using the idea of fundamental theorem of calculus, this will make you can see that a lot faster. Okay with this? And the next one, if in the definite integral your lower limit and upper limit is the same, that means what? 0. That I can basically tell you with this, like, you have a graph, and if you are basically talking about your lower limit and upper limit is the same thing, you are not even forming a rectangle. So therefore, there is no area of a rectangle. Does it make sense if I explain it to you that way? So there's no area at all in this case, so 0 area. And if you are talking about a constant, well, that's easy to show to you. If you have a constant functions, that means if your function is constant, that basically means a horizontal line. So if you are talking about area, right? Area under the horizontal line on this interval a to b, that's basically you are talking about what? The area of a rectangle. So what is the width? That would be b minus a. And what is the height? It's always going to be c. So that's how you got c times b minus a. Do we follow? And the rest is basically follow from the Riemann sum idea from the definitions. So this is a quick, showing of geometrically, not rigorously, geometrically showing why this was true. And integral of sum of two functions is the same thing as integral of the first function plus the second function. That's basically coming from the formula, the summation notation, right? And with the Riemann sum definition of definite integral together. So this one, if it is an integral of constant times a function, then I can basically factor out that constant and then integrate the function first, and then multiply by whatever the value that we got, and multiply by the function of the constant. And similarly, this is a. Let me illustrate with the graph on this part. So let's say you have a functions f right here, and here's my interval from a to b. This area from interval to a to b is the same thing as when you're saying that, right? Evaluating this area, so you notice that right here, from a to c. Then adding with after evaluating this area, which is c to b. So this two area is same thing as what this whole entire area. That's what this integral notation is talking about. So this is intuitively, geometrically shown quickly, right? And of course, all of these can be, use the definitions of definite integral to rewrite and then derive. Are we okay with that? And then after that, it's more of the inequality form. If the function value is always greater than 0 between the integral a to b, then the definite integral, right? The value of the definite integral will be also greater than 0. Well, that's something that I pointed out in the beginning of 4.2. Right? When we talk about in 4.1 and the homework that you do in 4.1, most of the function will be given to you with the interval that only above the x-axis. So therefore, if the function value is greater than 0 within this interval, so your area under the curve will be also a positive area. That's basically what it's talking about. Does that make sense? Now, next one is a comparison one. So I'm going to show you with the graph. If the function f, here's the function f, and here's function g. So within this interval a to b, and function f is always bigger than function g, then clearly the area under the curve of g functions, that will be smaller than what? The area under the curve of this whole f functions. So that's why right here you see that integral from a to b of f of x dx is greater than, that value is greater than integral from a to b of what? G of x dx. So, geometrically you can, see that, but when you actually deriving it, it's not that, quick. Okay. So lastly, if the function is bounded between two values, then the integral from a to b of that function is also bounded between what? These two areas. That I can show you easily also right here. Let's say here's my functions f. So here's the area from a to b, right? Integral from a to b. So the area under the curve will be all of this. Okay? Now, what we are saying is, here's a value m that is smaller than, it will be always smaller than, the function value within this interval. Now, let me draw a different color. Here's m, and it is always smaller than. So that means the area of this function's m, right? The area will be what? This rectangle right here. That is basically what? B minus a times with this height right here. So that's what we got. And definitely this area in pink that I shaded is smaller than what? The area of the yellow one that I shaded. And the other one, let's say this function is smaller than a big M, some constant function in that particular interval. Then now you can see that this area right here in blue is definitely what? Bigger than the area in yellow. So therefore, this becomes my upper bound. So that's basically what this, inequality portion is talking about. Why am I talking about this? This is very, these will be used, right, when we talk about in like proving some theorems later on. But for now, what we are interested in is like more of the first few, properties. So, is there any questions before I move on and then finish up this sections? Okay. Let me just put these. So the first example. What is my answer is going to be in this case? Zero, because integral of lower limit 13 to upper limit 13 of this function dx, even though we don't know how to integrate, right, this function yet, but the property tells us if the lower limit and upper limit is the same thing, that means it doesn't even have an area. So it will be E0. Next one. Here is the given. Okay. Given that integral from 6 to negative 10 of f of x dx is equal to 23, and integral from negative 10 to 6 of g of x dx is negative 9, and we want to find out the integral from negative 10 to 6 of 2 times f of x minus 10 g of x. So that means we need to use the property to find out what this value is. So first up, the integral that we are interested in to evaluate is from negative 10 to 6. So what we need to do is we need to look at this one. Rewrite it a little bit. So if I rewrite it from integral from negative 10 to 6 of f of x dx, that basically tells me the value, see, from this first one, the value will have what? An extra negative number. So this is basically going to equal to negative 23. Are we all okay with this? Any questions before I move on? All right. So if you don't have questions, then I'm going to move on to the actual questions. So right here, first I'm going to use sum and difference to rewrite it. So this will be integral from -10 to 6 of 2 times f of x minus integral from -10 to 6, 10 times g of x. And if you write it like this, at the end d of x, that is wrong. Right? When you split it into integral of sum to sum of the integrals, then each integral have their independent variable. So make sure you don't forget that. Continuing this, constant time the function, so I can print this constant out as a multiple, -10 to 6 of f of x dx. -10 times integral from -10 to 6 of g of x dx. Now I do have value for each one, right? So the first one, -10 to 6 of f of x, that is -23, minus 10 times for the g of x part, integral from -10 to 6 of g of x, that is -9. So that gives us my final answer, -46
Plus 90.
plus 90.
It's 56.
So that will give me +40. Any questions? So we don't know how to take integral yet, okay? On these complicated function like the first example number 4, sine and cosine, we don't know how yet. And for example number 5 doesn't even give you the functions. So we can, both of those two examples we were able to use with the formulas right here, right? The properties. So let's take a look at on the last one. Evaluating the absolute value integral. So how do we do this? We haven't even learned about evaluating, this yet. You need to remember the very fundamental idea of this definite integral that I pointed out way in the beginning of this session is the net area under the curve. So that basically is by saying that to find out the value of the definite integral from 0 to 10 of absolute value of x minus 5 dx is basically looking for the area. Right? So at this point, that's the only way that I can approach and think about it. So what I can do is first, I can easily graph my functions, right? My functions, f of x, absolute value of mine, x minus 5. That is basically talking about a V shape that moved to the right 5 units. So now this is my interval 0 and this is my upper bound 10, right? Lower bound and upper bound. So that's why I put it right from here 0 to 10. That's what I want to look at my graph. When x is 0, my function is what? 5. My function value is 5. When x is 5, my function value is 0. When x is 10, 10 minus 5 is 5. So we are talking about, here is my V shape, the graph of this absolute value 5 from 0 to 10. And when we talk about the area, right, under the curve, that is basically what? Talking about this area right here, which is the area of a triangle, and this area right here, right? Because we cut it off right here. So finding out this integral, the value of this definite integral, is basically same thing as finding out these two areas. So now this is how we're going to approach. Any questions before I move on to we follow the key point that I'm trying to remake again. So this is basically equal to area 1, area 2, right? Area 1 plus area 2. What is area 1? The triangle. 1/2 my base, that is 5, times with my height, that's also 5. Plus, same thing, 5 to 10 is also what? 5. So 1/2 base times the height. So which is equal to 1/2 25, 1/2 25, which is going to be what? A full 25. So this is going to be unit square, right? So this is basically what? The using the fundamental idea of this definite integral, definitions of definite integral, to find the value of it when we don't know, right? While we don't know how to integrate at all yet. So that concludes this section.